So, a couple of things here to get us started. First thing to remind you of is the class survey. Remember, there's a link in D2L under class survey. It takes you out, and you take I think it's 14 questions. This is due on the 25th. That's this Friday at, I think I got it set at 11:30 p.m. Okay, here's the thing. It never did give you the cute dog. It never did do anything. It did come up and tell you completed it, but by the time you got ready to make a screenshot, it already disappeared. So a lot of you just sent me that last thing. We're good. Everything's good. All right? And so whenever you hit the bottom and you submit, whatever that next page that shows up, give me a little screenshot of it, something. You're going to put that in the Dropbox in D2L, right? That's the first thing. Second thing, our first test is on Tuesday, the 24th. Okay? And I'm going to be realistic with us, and we're looking at this, chapters 1 through 5. And I'm not going to guarantee you we're going to get all the way through 5 on Thursday. So wherever we stop, that's where wherever I end up on Thursday, I'm going to tell you, okay, this is where we're going to stop. And the test is over 1 through 5 and 5 to where we stop. Okay? You're going to need to bring with you a calculator. We don't use the cell phone as a calculator. Makes me a little nervous. You need an ETSU ID or some form of ID, because there's going to be some people show up here that I have never seen or the person in Johnson City's never seen. The third thing is you need to bring your formulas and tables. Remember, you're going to have that table A that you just used over the weekend, and at the beginning of those 6 pages, there's some formula sheets there that you can have. All right? That's all we're going to need for the test. The test is going to be 40 questions. It's multiple choice. It's going to be A, B, C, and D, so on and so forth. All
Dr.
right?
Myers?
Pardon me?
Sorry, question from the Johnson City group here. You wrote down that the test is on Tuesday, 9/24, but today's Tuesday, 9/22.
Oh, that's not good, is it? Look, it was a long weekend.
Okay, that's better. Thank you.
No. When I do shit like that, you got to speak up because you got no idea what I'm talking about. Yeah. Okay. Now, here's the other thing. You folks in Johnson City, next Tuesday, you're going to be in Sam Wilson. You folks are going to be here. I have sent an email to the 990 students, the streaming students. And if you told me Johnson City or if you told me Kingsport, here we're in room 232. You're going to come take it with the rest of us. And if you told me Johnson City, you're going to go to Wharf Pickle, room 517. If you told me a Proctor, some of you have been sending me the stuff, that's fine. The Proctor is no problem. We're going to take care of that too. That should take care of everything about the tests. Now, here's the other thing I'm going to do for you. Thursday, when we're done with class, and like probably 9:30, 10 o'clock Thursday night, students always want to know if you're going to post a study guide or you're going to review. Well, I'm not going to review, and I hate the term study guide. So what I'm going to do is I'm going to post you some thoughts I have for test 1. The things that you need to be able to do and the things that we've done and stuff like that. And the reason I'm waiting until Thursday is it depends on where we get in Chapter 5 on what's there. And I'll tell you this on Thursday, and I'm going to put it in D2L, and it's under the syllabus, and it'll say thoughts for test 1. All right? That's 2 things. One more. Look, I know that we're having a test on the Tuesday, next Tuesday. But I want, and I don't usually do this to you. Okay? I know I haven't said anything about picking the one up from the other for this due today. We're going to do that in a minute. What I wanted to do is I wanted you to look at a few problems here out of Chapter 4. Look, these 2 here are multiple choice. You'll just go through and answer them. This one here, This problem here, you're going to need a scatter plot, right? We talked about that last week, so that's nothing really new. You're going to use Minitab to do that. And then there's one other thing you need in this particular problem that is going to be talked about tonight, and it's the correlation. This is going to be a calculation that we're going to work on tonight. And the correlation is always denoted by a little r. So we're going to talk about that, and you're going to use Minitab to give me the scatter plot and the correlation. I don't figure 2 multiple choice questions and 1 question that requires a scatter plot and some little calculation that Minitab is going to do for you to be too much to have happen between now and Thursday, right? The other thing I'm going to do is, remember I've been posting the homework solutions all along. Homework solutions 1 up there, 2's up there. The 1 for 3 will be posted on Thursday. Since this homework is due on Thursday, and we're having a test on Tuesday, I will post the homework solutions to homework 4 like Friday evening, like at 9 o'clock, and that way you can look at them before the test. Okay? That seems fair enough to me because you're not going to get this homework back before you take the test. That's the way I would like to handle that. Okay? That's all my little stuff to get started here today. All right? Now, the last thing I told you on Thursday was adding a categorical variable to a scatter plot. Okay? So the deal is you got groups in your data. And how are we going to get those groups into a scatter plot where you're looking, the reason you're making the scatter plot is because you're looking at the relationship between 2 quantitative variables. Well, adding a categorical variable means change the symbol, or change the color. That was if you were doing it by hand. Minitab is going to do both of those things for us. Okay? So I want to show you how to do that. I mean, we've seen how to make a scatter plot. What do I got to do to add a categorical variable? What do I got to do to put groups in the scatter plot? So the problem I was going to look at was on page 110. It's problem 4.9 there under the apply your knowledge. It says death by intent. The data described in exercise 4.4, we didn't talk about that one, it's okay, also indicated that the homicide rates for some counties should be treated with caution because of low counts. Okay, so you got a table here. And what they've got here, if I remember right, there are 26 counties in Ohio. All right? And they have three things measured on them. One is the homicide rate, the other one is the suicide rate, and then the other one is did they issue a caution about this, right? Yes or no. That's your categorical variable here. It says make a scatter plot of homicide rate versus suicide rate. Now you see that language? It's the verses that's catching my eye here. When somebody tells you that, it's always Y versus X. So they're trying to tell you that the homicide rate should be your response and the suicide rate should be your explanatory, or if you like, the homicide rate should be your Y and the suicide rate should be your X. Anytime it's a versus, it's always the Y versus the X. That's standard math language there. It says, make a scatter plot of homicide rate versus suicide rate for all 26 counties. Use separate symbols to distinguish counties for which the homicide rate is to be treated with caution from those that are not, right? So in other words, introduce this categorical variable there. So I got Minitab up for us. I got to find this file. We're in chapter 4 here, right? The title of this file is Death 2. Nice. The dude's good at naming them. Now look, that's just a lazy man's way. Somebody put that table in there for us, right? You got 26 counties, you got the homicide rate, suicide rate, and whether they should be something should be treated with caution. Now here's what I want to do. The first thing I'm going to do is I'm just going to make a straight scatter plot and not put any categorical variable on there. All right? So that's just a simple one. Remember, it was your homicide rate versus your suicide rate. That's your Y versus your X. You want the homicide rate, then you want the suicide rate. I got a question for you. Do you see anything? Okay, we're looking at a scatter plot here, so there's supposed to be three things we're supposed to talk about, and I always start with the direction. Do we see a positive association, or do we see a negative association? Damn. I don't see too much of anything here, folks. Right? I see a pile of points all scattered about. I guess if you held me and said, tell me something, I might tell you see a little positive association here. Not a good one, right? Not a good one. I mean, it looks like if you had a higher suicide rate, you have a higher homicide rate, but that don't hold for all these points. I'm just saying, if you force me, I might tell you a little positive association here. If you let me get away with what I really want to tell you is, look, dude, I don't see nothing. I see a pile of points. We made the scatter plot, right? Okay, so now let's introduce that variable about caution, all right? So I'm going to get rid of this one. I'm going to come back here to graph, scatter plot. Now you want with the groups, right? We just did the simple one. I want with groups. We're going to put groups on here. Now, the Y is still the homicide. The X is still a suicide. You see there's this extra box down here that says, what's the categorical variable for the grouping, right? What's the categorical variable you're looking at? And here it is. It's the yes or no, right? It's the caution. So not only does Minitab change the color, hell, it changes the symbol, right? You notice the yes is the little red squares, and the no's are the little blue dots, right? Now, what do you see now? Separate them, right? Look at the blue dots. Those are the ones that said no. The red ones said yes. Don't they all look scattered within their own little groups? Yeah, right? Do you see a difference here? Do you see how all the red ones are down here and all the blue ones are up here? So the ones that had said caution, right, that you should treat this as caution, it looks like they had a lower homicide rate in general, right? Where the ones that said no, looks like they have a higher homicide rate. Look, I'm going to be honest with you. You let me look at it all together, I don't see too much. You let me put these little groups on there, I still don't see too much, other than when I start looking at the groups, the red ones are on the bottom, right? And the blue ones are on the top. It looks like the ones that had no had a higher homicide rate. Looks like the ones that said yes had a lower homicide rate. I don't really see any positive, negative directions, and I'm definitely not going to talk to you about no form. I don't see nothing but a pile. All right? This dude screwed the book up bad. He couldn't come up with a better example than this, but that's what he's got. You know, the red ones are down here, the blue ones are up there. That's what I see. A higher homicide rate up here, a lower homicide rate down here. The suicide rate, hell, it's all over the place for both of them, right? It's the homicide rate I see a difference in. Well, remember what the yes or the no meant. Homicide rates for some counties should be treated with caution because of low counts. Yeah. Looks like they were lower. Other than that, I don't see none. Okay? Now, that's how you do it. One more time. You're going to have to do this later. Not so much for me, but remember we got that project that you're doing the survey for. That was scatter plot, and I chose the groups. And then you still have your Y and your X, and then there'll be some categorical variable that you'll put in, and it'll, if there was more than 2 categories, you would have 3 symbols in 3 different colors. If there was 4 groups in your categorical variable, there'd be 4 symbols in 4 colors. They always change the color, and they always change the symbol both for you, right? And then you notice, when I did this, up here in the right-hand corner, they let you know what the symbols stand for in terms of your categorical variable. That's how you add one. That simple, okay? Now, the rest of this chapter is going to help me with problems like that one right there. When I look there and I just see, and I maybe a pile of points ain't the right idea, because, I could tell you it's a pile of crap I see there. There's just all these little dots, right? This next little part is going to help me with that. Here's our calculation. Remember, there's only one graph here, scatter plot. As far as I'm concerned, in this chapter, there's only one calculation. And it's said to be talking about measuring linear association. Remember, we talk about association, we talk about a relationship. In the middle of the chapter, the book has changed its term on you, right? Remember, we talked about a linear, we always talk about a relationship. I always keep writing in blue above it, association. Association, relationship, all the same thing to us, right? So when you talk about measuring linear association, the calculation we do is correlation. That's our guy. Now, I'm going to circle something for you here. It wasn't about any other form, right? We're talking about the form being linear here. I told you last Thursday we like linear form. We're always looking to see if our relationship is linear, right? Do we see a line? Okay? Well, correlation only tells us about a linear relationship. It won't tell you anything about curved. It won't tell you anything about a pile of points. It's always telling you something about your relationship being linear or not, or how linear is it. Now, on the bottom of page 111, there's a box there. It says correlation. The correlation measures the direction and strength of a linear relationship between two quantitative variables. Now, strength and direction of a linear association. Now I'm going to start numbering things for you. We know what form we are looking at. We're looking to see if we have a linear form. The other two things you're supposed to tell me about is strength and the direction. So when you start telling me about correlation, you're telling me about all three. You're telling me the form you're checking is linear, and then what we calculate is going to tell you something about the strength of the linear relationship and the direction, right? Whether it's positive or negative. Here's the thing. I got a big formula on the top of page 112. I'm going to write it down just so, I'm in the class here. Okay, the teacher did write it down for you. And I'm not going to use it, and I don't have a lot to say about it. But when you think about what the formula is here, it looks like this. It's always denoted by a little r. That's your correlation. And you've got 1 over n minus 1, so we're taking some kind of average here. And then, everybody remember what that capital sigma means? It means add all these little pieces together. We're going to take the x. Now, you remember, you got a set of individuals here in this chapter. You have two quantitative variables measured on them. When you made a scatter plot, you called one of the variables x and the other variable y, right? So there's a mean of the x's, that's the x bar. There's a standard deviation of the x's. Remember, we use s for standard deviation. That's s sub x. And then you're going to do the same thing for the y's. Now, you just spent a whole bunch of time this weekend working on these normal distributions and calculating the z-scores. Remember, x minus mu divided by sigma? Yeah? Does everybody see these two pieces here? This one and this one? Oh, I know it's not a mu and it's not a sigma, but you're going to take each x value and you're going to subtract off the mean of the x's and divide by the standard deviation. You're standardizing. You're not standardizing with what came from the normal curve. You're standardizing with what you're calculating from the data. And the same thing with the y's. You're standardizing. Now, the only reason I point this out to you is, okay, we could be looking at the relationship between heights and weights. Heights could be measured in inches. Weights could be measured in pounds. As soon as I standardize everything, the units all disappear, right? And you're measuring the number of standard deviations observations our way. So R has no units. The other thing about R is, not only does it have no units because you standardize, you do understand if I was doing heights and weights, and I had the heights measured in inches and the weights measured in pounds, and I calculate and get a number here. And all of a sudden I changed, instead of measuring the heights in inches, maybe I measured in centimeters and I measure the weights in kilograms. Do I want this correlation calculation to change because I changed units? No. So the other thing is changing units does not change your correlation. So I don't care if things are measured in inches and pounds or centimeters and kilograms, going from one set of units to the other set of units, that R still stays the same, and it's because of your standardizing there. I understand that's not the z-score you used in Chapter 3, but it is standardizing, and you're standardizing with the mean and standard deviations from the data. All right? Now, here's the thing. I know I've done that to you twice now. I did it with the standard deviation back in Chapter 2. I'm doing it with the correlation for you here on Chapter 4. And you've seen the kind of things I've asked you. If you need the standard deviation out of Chapter 2, I give it to you. If you need the correlation, I will give it to you on the test. Right? The calculation's not the big deal here. It's what it tells me after I've done the calculation. All right? So just like I did to you in the standard deviation, I listed facts, right? And said, don't worry, we'll calculate it. You know, we'll have the software or we'll give it to you. I'm going to do the same thing to you here with the correlation. Right? So, it works like this. Facts. The first fact is R makes no distinction between explanatory and response variables. Translation: the correlation does not care that you called one variable the explanatory and the other the response. In other words, you got an X and you got a Y. If you flip-flopped them, the correlation is going to come back to you exactly the same. It does not care that you made that distinction in your scatter plot. Remember, I'm going to give it to you like this. Both variables are quantitative. I cannot, and I repeat, I cannot calculate the correlation between a person's gender and their height. I have a little problem getting that little M or F in the formula there. Right? Both of the variables are quantitative here. Now, 3 and 4 is the biggie. 3. Now, number 3 is about the direction. And it's very, very simple here. That if the correlation comes back and it's positive, it's a positive number, right? This is a number. You get a positive number, you have a positive association. If R comes back to be negative, you got a negative association. Right? So the sign of the correlation tells you the direction. Remember, that was one of the two things it was supposed to do for me. Okay? Now you notice I left out R being 0 here, correct? If R is positive, positive association. If R is negative, you got a negative association. The sign tells you the direction. And then 4 is going to tell you the strength. This is how I think about this. Now, the fact is that the correlation, if somebody tells you they calculated the correlation and they got 2.43, no they didn't. Or they got a negative 7.62, no they didn't. The correlation runs between -1 and 1. Nothing outside of there. Now, the closer R is to plus or minus 1, the extremes. Okay? The stronger the linear association. Right? So, I always got this little number line sitting in front of me in this class, and I'm at minus 1 and 1. The closer you get to minus 1 or the closer you get to 1, the stronger the linear relationship is. The better you see a line in the scatter plot. If R is equal to plus or minus 1, exactly plus or minus 1, you have a perfect linear association, perfect linear relationship. In other words, you can actually draw a line that passes through all the points in the scatter plot. Okay, so here's the way I do it without me writing it down. All right? Minus 1 plus 1, the point is you're seeing a 1. Minus is telling you you're seeing negative association. The plus 1 is telling you you're seeing a positive. Those are perfect. Right? The closer you are to minus 1 or 1, the stronger it is. The closer you are to 0, the weaker it gets. Let's do it like this. At R equals 0, you don't have a linear relationship. You don't see a line. You're wasting your time. As you start moving away, right? And I'm probably out here at like 0.3, minus 0.3 and 0.3. Now I'm weak. Right? Minus 0.5 and 0.5, I'm moderate. And then as I start going out, I start talking, you're stronger, very strong as closer you get to minus 1 or 1. At 0, you're wasting your time. At 0.05, you're wasting your time. Right? The closer you are to 0, you don't have a linear relationship. You don't have a linear association. Now, here's kind of what I wanted to do. Okay? I'm not going to calculate any of these by hand. Now, you remember this one about homicide and suicide rates? And I told you I just saw a big pile of points? Okay? If I come here to stat basic statistics, remember that's where you do the display descriptive statistics to give you the 5-number summary, means, standard deviations, and all that, right? You see down here almost at the bottom, correlation. That's our guy. That's our little R here. Now, it says method. This is the Pearson correlation. Our book just calls it the correlation. I always uncheck this little display p-values. I don't care anything about that. And you see that window? It wants to know, what are your variables? What's your two variables here? Well, the two variables you got are homicide rate and... Did anybody ask you which one was the y and which one was the x? No. Correlation doesn't care. It just wants two quantitative variables. It doesn't make any difference you had one as an x and one as a y. One is explanatory, the other is response. And then we click OK. I got 0.230. Now there's the scatter plot that matches up with that correlation being 0.230. Remember I told you if you forced me I saw a little bit of a positive association, right, going out? The correlation is confirming that he saw a little bit of positive association. A lot? No. A little bit? Yeah. Everybody understand what I'm talking about? How strong is this linear relationship? Oh no, this is very weak, right? Because you're close, at 0.23, you're close to 0, right? So you have a weak, positive, linear relationship in that problem. I'm not shocked that when I stand here and look at this, that I have a hard time picking out a linear form. You know, I gave you a little bit that I could see some positive there, but other than that, I don't see no linear form. Why? Well, the correlation is confirming what you saw. He didn't see anything. That's what I was telling you earlier. Okay? Now, one of the other ones I would like to do, you remember we talked about the manatees and the boats? Yeah, can we get the one that looks halfway decent here? And I got to find that file. No, you don't have it. I told you the dude screwed the chapter up. Remember, he didn't give me the file. All the files, and he don't give me that one. What was the other one we talked about? The percent of graduates taking the SAT, right? Let's look at that one. Remember, I told you saw a negative association. That's the one we started this chapter with. I just want to calculate the correlation for you. It doesn't matter which order I do them in. Now, you see the correlation is negative 0.88, right? Let's see what the scatter plot looked like. The scatter plot. What was we trying to do? We was trying to use percent taking to said something about the math SAT score, right, for the state. So the math SAT was the Y, percent taking was the X. Does the negative part of the correlation make sense to you? I saw a negative association, right? They went from upper left to lower right. How strong is this? How close am I? Look, you're only going to be numbers between -1 and 1. You're at negative 0.88. Are we close to -1? Yeah, we got a strong, positive, linear relationship here. Okay? You're not going to get a correlation of -67. -0.88 is close to -1. That's a strong, negative, linear relationship. We looked at it, right? And I told you that I would do better about the strength and the form. Well, we're looking to see if it's linear. Now, one of the other ones we did last week was we did this fuel and consumption and all that. What example was that? 4.8. And we were looking to see, I always like to give you the correlation first, and then I'll throw up the scatter plot. It was a negative 1.72. How strong was it? That's as bad as you've seen. Oh, I understand the other one was positive 0.23, but you're at negative 1.72. Do we have a linear relationship? And the answer is, if you're going to tell me we do, it's like nothing. All right? Because if I make the graph of that one, which way was I supposed to go here? If I remember right, the fuel was the Y and the speed was the X. Does anybody see a linear relationship in that picture? Well, man, last Thursday gave me parabolic, right? We're seeing a curve. Is the correlation confirming that for you? Yeah. Right? You're checking yourself out with what you're seeing in the scatter plot. The correlation's confirming it. Negative association? Okay. Well, the hell, it ain't no good. There's no line there. The correlation is trying to tell you that. Now, the reason I brought this one back up, because next Tuesday I like to put this question on your test. Now, it doesn't really matter to me what two variables I have in mind, but the question I've used in the past is this. It turns out that there's a relationship between the temperature that you bake brownies at and the quality, like on a scale of 0 through 5. Yeah? But it turns out the correlation's -0.05. And so what I want to know is, does that correlation being -0.05, does that mean you don't have a relationship? No. It means you don't have a linear relationship. You might have a relationship of another form. Because I stand here for 10 minutes and I preach to you about linear this, linear that, linear, and we use the correlation to measure strength and direction of linear. The correlation comes back to you close to 0. Does that mean you don't have a relationship? No, hell, you got to look at the scatter plot. It can be curved, right? In this case, we're curved up like that. I don't know. With that in mind, I'm going to your homework for a second. I'm hoping it's still back here. It's probably not. I'm on page 119, and I'm looking at 4.19. I'm looking at problem 19. It says if the correlation between two variables is close to 0, you can conclude that a scatter plot would show A, a strong straight line pattern, a cloud of points with no visible pattern, C, no straight line pattern, but there might be a strong pattern of another form. The dude put that in there? I'm going to tell you it's not A. Right? So there's one that gives me something close to 0. Right? If you give me something that looks like this, now I'm going to draw you a picture. I would expect R to be close to 0 there too. Remember, it's checking linear. You see a line there? No. All right. Remember my squirrely lines? Now, what about this? Let's say I gave you a question and it looked like this. What do you expect R to be? First off, do you expect it to be positive or negative? Positive. Do you expect it to be close to 1 or do you expect it to be close to 0? In other words, if I had to pick, I'm thinking, right? Look, I'm drawing the pictures for you that's in this little part about the book in the book here. So that's 1. Let me ask you this. You expecting positive or negative? That's a negative association, right? Upper left to lower right. Now, that one's the points are actually closer. We're closer to 1, right? You give me a thick magic marker, I'll draw a line through them all. Yeah? So that's the deal. The closer you are to -1 or 1, when you look at the scatter plot, you will see the line defined better. You'll see a line forming. Until I get to something like that, and then the next step is just put them all on a line, right? Then you're perfect. The minus means you got a negative association. The plus means you got a positive association. That's all that's going on here, folks. All right? If I get some other pattern, and let's do it like this. If your correlation is close to 0, don't tell me you don't have a relationship. It might be another form. It might be a cloud of points. I don't know, right? You have to check the scatter plot to see. And I've been known to put that kind of question on test about every semester like that. I'm thinking the dude that wrote, forget it, I give. Now, I'm going to give you some cautions here, right? I gave you some facts, no distinction, so on and so forth. My cautions are this way. Okay? The first one is only linear. It won't tell you about any other form. It's only to check in to see if you have a line. 2, strongly influenced by outliers. Does everybody understand why? What else do we know that is strongly influenced by outliers? The mean, the standard deviation, right? Well, you've got 2 quantitative variables. You've got a mean of the x's, a mean of the y's, standard deviation of the x's, standard deviation of the y's. So if you see outliers in your data set, this correlation is going to be strongly influenced by them because you use those other 4 things to calculate the correlation. 3, R is not a complete summary. In other words, just calculating the correlation and telling everybody, oh, here's all you need. No. If you're going to tell somebody about a relationship between two quantitative variables, give them the scatter plot. Give them the means of both your variables, right? Whatever's on the x and whatever's on the y. Give them the standard deviation of both your variables. And also include the correlation. Give them that's a complete summary about a relationship. Scatter plot, means and standard deviations, and the correlation to tell me whether I'm looking at linear or not. And then I got one other little thought here. I've had this thought with you before, but now there's two variables to be concerned about. Adding the same number to x, y, or both does not change your correlation. Remember how in chapter 3, I wanted to take all the observations and add and subtract? Well, I'm just saying adding. Subtracting is the same thing. Let me ask you this. Let's say you got your scatter plot, and you take your x variable, right, the one that's on the x-axis, and you take every observation, every piece of data, and you add 5 to every x value. What did you just do to the scatter plot? You just picked it up and you slid it down by 5, didn't you? What about if you just added 5 to all the y's? You picked it up and moved everything up by 5, yes? What about if you added 5 to everybody in sight? You picked it up, moved it over, and you moved it up. Did I change the direction? Did I change the strength? Did I change the form? I'm just moving the picture around on the scatter plot. That's all I'm doing. That's the reason adding the same number to the x, y, or both does not change your correlation here. Okay? Now, I got to do one more. And it's just me. And it's because I always do this one. And I'm on page 117. And there's 413. I mean, I showed you one that looked like this already, but here's the deal. The gas mileage of an automobile first increases and then decreases as speed increases. Suppose that this relationship is very regular, as shown by the following data on speed, miles per hour, and mileage, miles per gallon. Make a skim plot of mileage versus speed. Versus, see that again? Remember, y versus x? Yep. Let's make a scatter plot for that data. The data here is miles per gallon. So I come over here, we find that one. That's 413. We want to make a scatter plot. We want to make a scatter plot of mileage versus speed. Mileage is my y, speed is my x. Anybody see any linear form here? Does anybody see a curve? Okay, let's calculate the correlation and see what happens. All right? Anybody expecting the correlation to be close to plus or minus 1? No, you're not. So we come up here to stat, basic statistics, correlation, speed, miles per gallon. Anybody shocked the correlation come back with 0? Does that mean you don't have a relationship? No, it means you don't have a linear relationship. The scatter plot is showing you have a perfect curve. You give me like a little thing there, I can just draw right through there, right? Look, you're not going to calculate the correlation by hand. So you got to be aware of these kind of things like this, right? It tells you two things. It tells you the strength and the direction, and the catch is it's only of a linear relationship or a linear association. It tells you nothing about curves. It tells you nothing about a cloud of points. Nothing. All right? Now, you also got to know that you got to have two quantitative variables. It doesn't have any units. I'm on page 124. So, once you get the correlation, then you have a feel about what's the strength and direction of a linear relationship or whether you have one or not. And then you see a problem like 4.39 on page 124. It says, each of the following statements contains a blunder. Explain in each case what is wrong. There's a high correlation between the sex of American workers and their income. What's wrong with that statement? That's a statement about correlation, right? About the sex of American worker and their income. Sex is their gender, right? That's male or female. You don't have two quantitative variables. You got one that is categorical. Part B, we found a high correlation. R is equal to 1.09. I ain't going to read no further. Can you get a correlation bigger than 1? Nope. Right? And then there's part C. The correlation between height and weight of the subjects was R was 0.063 centimeters per kilogram. What's wrong with that one? There's nothing wrong with R being 0.63, right? You got a positive, moderate relationship. Where in the hell did units come from? Centimeters per kilograms? The correlation never has a unit. So you want to know how you turn that into a multiple choice question? I give you 3 like that, and I give you a correct one. And I ask you, which is the following is a correct statement about the correlation? Right? 2 quantitative variables between -1 and 1, no units. Those are the facts. That's the reason I went and found that problem for you. That's how things show up here. All right? Changing the units of the original variables doesn't change R. Remember, we standardized. Okay? So the problem you're going to do for homework, right, there's 2 multiple choice questions. I don't think I did anything strange to you there. What was it, 414 and 415? Right? And then the other problem is 4.28. And it's about sparrowhawk colonies, and it's on page 121. I mean, it tells you how to set it up. It tells you what to make the response, which one to make the explanatory. It asks you to calculate the correlation. We saw how to do that. And then it asks you a question about what you're seeing and what the correlation is telling you in 4.28, right? Okay? Now, the next chapter is a continuation. This could have all been in one. Scatterplot, correlation, in this chapter 5 could have all been in one chapter here. All right? So, this chapter 5, the title of it is Regression. Okay? Now, here's the deal. Okay? Throughout all the way through chapter 5, what we're interested in is the linear relationship between two quantitative variables. Now, I'm going to circle this. Throughout this whole chapter, your form, that's what we're looking at. We're looking to see if we have that form. We're thinking about the linear form. Okay? Now, if we think we see a linear form, if the correlation is telling us that we see a linear form, okay, what we want to do is we want to summarize the linear form by drawing a line on the scatter plot. If you don't like the term summarize, have I done this to you before this semester? Chapter 3, right? We had a histogram. The pattern was so nice that we could draw in a smooth curve, a density curve, right? We approximated what we saw in the histogram by drawing in a smooth curve, a density curve. Well, now we're looking at linear forms, right? We're looking at linear relationships. Well, if we think we see that, then we want to summarize the linear form, that linear pattern, by drawing a line on the scatter plot. All right? And so that brings us to regression lines. Okay? The line we're going to talk about, that's what it is. It's a regression line. And I don't know how much algebra you remember. It don't really matter. Regression line is on page 127 here. That's where the definition is. That's where the little box is on the bottom of the page. I'm going to read it to you because I'm kind of interested in how this all gets set up here. A regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. It's trying to tell you the regression line, you got to call one the response and you got to call one the explanatory, right? You're going to make that distinction here. It says we often use a regression line to predict the value of y for a given value of x when we believe the relationship between y and x is linear. Okay, so there's two ways we're going to do this. The setting. Okay. Use one variable to predict the other variable. Yeah, I know that was the second one in the box, but that's what I always think about when I think about this regression and what's going on in this chapter is the reason I'm doing this is because I want to use one variable to predict the other. Now, just so you remember, in chapter 4, this is your explanatory. This is your response. Right? The variable we use to make the prediction is your explanatory, your x. The variable that we're trying to predict is your response variable or your y there, right? Just to remind you that. So what I'm trying to tell you is I need that distinction. I need one to be the explanatory and the other one to be the response. And the other one is, right, use one to predict the other. See how one variable changes as we change the value of the other. Now again, we want to see how one variable changes. This one here is going to be your response. This one here is your explanatory, right? The one where you're changing its value. Now, the reason I reminded you of both of these is because if we're going to do this idea of this regression line, putting this line on our scatter plot, we have to have explanatory and response distinction. Right, there were some things we looked at in chapter 4, and you're going to see that when you work some problems, and even when you do the learning curve, that nobody made that distinction. Call one x, call one y. Well, here, I'm telling you, the two places this is going to work for us is making a prediction or seeing how one variable changes when we change the value of the other. We got to have that distinction, right? We got to have explanatory and response distinction. You got to know which one goes on the x and which one goes on the y. Now, what I'm going to start with here is this example that the book has. It's 5.1. All right? Why? Because I get everything worked out for us. It says, why is it that some people find it easy to stay slim? Here following our 4-step process from page 63 is an account of a study that sheds some light on gaining weight. Okay. Some people don't gain weight even when they overeat. Really? They must be younger. Okay? Perhaps fidgeting and other non-exercise activity, like all of a sudden you just move around, you're hopping all over the place, explains why. Some people may spontaneously increase non-exercise activity when fed more. Okay? They measured, researchers deliberately overfed 16 healthy young adults for 8 weeks. Okay, so just so that we get everything laid out here, this example, 5.1, your individuals or what is it, 16 healthy adults? Or was it healthy young adults, wasn't it? Okay. I'm taking you all the way back to chapter 1. You got 16 healthy young adults. They overfed them. They measured fat gain in kilograms. Fat gain, that's one quantitative variable. That was measured in kilograms, units. Right? And the other thing they measured was their, as an explanatory variable, change in energy use in calories from either the deliberate exercise, fidgeting, so on and so forth, and the like. So I think about this as what I want to call their non-exercise activity change. So they didn't deliberately go out and exercise. It's just all of a sudden you start overfeeding them and they're bouncing off the walls, moving all over the place, fidgeting and everything, right? And that was measured in calories. So we have two quantitative variables. Now you remember the researchers are thinking that the NEA change helps explain the fat gain, right? So they're trying to tell you that this is your explanatory. This is your response. So the response goes on the Y, the explanatory goes on the X. Okay? Now, they give me a set of data here. It says change in energy use was energy used measured the last day of the 8-week period minus energy. Yeah, okay. NEA change measured in calories. They got a table here. They got 16 individuals. They've got their NEA change in calories and their fat gain in kilograms. Now, I have a question. The first person in this table had a minus 94 NEA change and a fat gain of 4.2 kilograms. The second person had a minus 57 NEA change and a fat gain of 3.0. And the third person had a NEA change of minus 29 and a fat gain of 3.7. What can you tell me about those three folks? That's me. You overfeed me. My butt sits on the couch. I don't fidget. I don't move. I actually decrease my non-exercise activity. Right? That's the negative ones. Anything that shows up with an NEA change that is negative, that means these people actually decreased their non-exercise activity when you overfed them. You see all the rest of them are positive? These people actually increased their non-exercise activity. Right? Their non-exercise activity went up. It increased when you overfed them. Now, somebody's going to make a scatter plot for you. That's what's in figure 5.1. Right? Couple things to note here. The NEA, non-exercise activity change in calories, is on the X, explanatory variable. The fat gain in kilograms is on the Y. Okay? And then the question says, forget everything else for a second. Underneath that table, the question is, do people with larger increases in NEA change tend to gain less fat? What's the question asking you? The question is asking you, do you see a negative association here? Do you see from the upper left to the lower right? And the answer is, yeah, right? In that figure, I see a negative association. Everybody agree? Hell, they drew the line in for you. The line's going from upper left to lower right. The question's actually asking you, I mean, I can put it to you in their terms. Do people with larger increases in NEA change tend to gain less fat? What they're asking you is, if you increase a person's NEA change, did you decrease the fat gain? Translation, are you seeing a negative association? And the answer is yes to that question, right? That's all they're asking you there. Look, the linear form, that's a hell of an idea. And the strength, that's even a better idea. But when people start asking you questions about the relationship between these two quantitative variables, they're asking you, do you see an association, whether it's negative or positive? This time they're asking you, do you see a negative one? Yes, I do. Right? If I increase the NEA change, if I increase your X, what's going on? It's negative. I'm going to decrease a person's fat gain. Yeah? And then they throw the line on there. You see that line that's drawing on there? That is your regression line. Right? That's summarizing the linear form that we think we see. Okay? Now, what I'm going to do is I want to show you where they got all this stuff. All right? So I'm going to come back over here. I'm going to get rid of that. I'm going to come back here. I think I'm in chapter 5 now. Is that correct? I'm in chapter 5. I'm looking at something about fat gain. And I mean, I know I just keep adding things down here, but that's just that table that's in that example, right? There's those 16 individuals. You got the 3 lazy bums. NEA change decreased, right? We want to make a scatter plot. I want to make a scatter plot that looks like the one in the book here, all right? So I go to graph, scatter plot. Now, we've used a simple one. We've used the one with groups. You see the third one over that says with regression? Let's add the line. That's what it's going to do. It's going to put that regression line on there. We're going to do that one. Remember, we're thinking that the fat gain is your response. NEA change is the X. Look, I don't have to do anything about the regression line. This is going to put it on there for you. So if I click OK, that's the one that's in the book, folks. The regression line, we're trying to fit that to the data. Did you hear what I said? The regression line is always fit to the data. The data is not fit to the regression line. We fit the line to the data. We see a linear form. Oh, that little story right there makes a difference, right? We fit the line to the data. Statisticians get pissed off at me if I fit the data to the line. Right? The data comes first. We're looking for a linear form. We fit the line. Now, don't freak out about how the line got on there. We're not there yet. Right? I didn't tell you the equation of the line or anything yet. While we're here, let's calculate the correlation. Do you expect the correlation to be negative or positive? I'm hoping negative. Do you expect it to be close to -1, closer to 0? I'm expecting to be closer to -1, right? The form doesn't look too bad here. Especially when I draw the regression line in for you. Oh, I can see the line, yeah. Okay? So I'm going to go to stat. Remember, it's basic statistics. Correlation. Doesn't matter what order you put them in. Remember, correlation makes no distinction. I click OK. Anybody shocked? It's negative 0.779. It's a negative. It's linear. How strong is it? That's fairly strong, right? I can see it. Regression lines fit there. Now, the book does one other thing to you at this point. All right? I'm going to leave that there. Okay? And I'm going to come back over here. On this example with the NEA change and the fat gain, can I use that line? Remember what I wanted to do? Either I want to change one and see how the other one changes, which I've already said that to you out loud. Remember, if you increase the NEA change, you decrease the person's fat gain, right? Because you had a negative association. Now I want to make a prediction using the line. In other words, I would like to pick some non-exercise activity change. It doesn't have to be a person in the data set because you're not predicting anything. Hell, I just go read it. I just want to pick some NEA change. Now the book does 400. So I want to predict fat gain for an NEA change of 300 calories. Now, the way this works is when somebody wants you to make a prediction, they're going to give you a value of your explanatory variable. They're going to give you a value of X. And then you got to read the data. You got to read the scatter plot. You got to read the line and find out what does the line predict fat gain to be. Now, there is none of these 16 have exactly a plus 300 calorie change in NEA. Right? So this is the way this is used. So what we're going to do is, you see how the scatter plot looks? Down here is 300, and there sits your line. Yeah, well, I know there's dots all over the place. There's individuals, right? But now, when I want to make a prediction, I'm interested in the line. I'm going to read up, and I'm going to read across. What's that value get? Now, you're not going to get exact. Hell, you're eyeballing it, right? I'm going to read up, and I'm going to read over. I'm not doing the 400. I'm in the middle here. I'm going to go up 300, and I'm going to go across, and I'm going to come out something like 2.3, 2.4, maybe 2.5 kilograms, right? That's the best I can do. I'm going to read up to the line, and I'm going to read across, and I'm going to call this 2.4 kilograms. I mean, I might be way off eyeballing it, but, on a multiple choice test, you're not going to pick 2.2, 2.3, 2.4, 2.5. Right? You understand I'm something close to 2 here, yeah? So what the line is doing for us, we have predicted fat gain if we had an individual that have a plus 300 NEA change in calories. Now, you got to get used to that move there. Not so much me reading up and over, but me using the line to make a prediction. You notice I didn't even draw the little points on there. I could care less. I'm interested in the line. Yeah? Could I have predicted, was there anything special about 300? Was there anything special about 400? No, I picked 300, held the book, picked 400. Could I have picked 600? Could I have picked 550? Yeah? Could I have picked 900? Be careful. Be careful. See, 300, 400, 550, you have data around those values of X, right? Do I got any values out here with a 900? No, you don't want to do that. Could I have estimated for minus 100, minus 150? What about minus 300? Here's the deal. For your explanatory variable, you got a range of values in the data set. Here they range from whatever I got here. What is it? Minus 94 up to 690. We never, and I repeat, we never, ever predict outside that range because we don't know what happens outside of there. We had data here. We fit the line there. We never go this way, and we never go this way. So I wouldn't predict at minus 200, minus 300. I'm a little iffy at minus 150. I definitely wouldn't predict at 800, 850, 900, anything too big. You give me between minus 100 and 650, I'll predict all day long. I'll find your little spot here, read up, read across, and tell you the predicted fat gain. I won't predict outside. That's at the end of this chapter, but I just want to get that in your head. Don't do that. Okay? Now, here's the thing. This is a hell of an idea here. Okay, use the regression line. Look on the scatter plot, read up and over. It's a one-time deal. Okay? Now, you see on page 129, it says, review of straight lines. You know how you're always used to, maybe not used to seeing, you got this little formula that says y equals mx plus b? Yeah, get the b and the m out of your head. All right? They got their own symbols here. And the part is they mess with your b. Suppose that y is a response variable plotted on the vertical axis, y. And x is the explanatory variable plotted on the horizontal, the x. A straight line relating y to x has the equation of the form. The form looks like this. Y equals a plus b times x. And again, mark it, throw out the m and the b. You got a plus bx here. That's the form we always have, and they always use a and they always use b here. Now, b is your slope. I don't want to get too mathematical on you, but b is the coefficient in front of the variable x. B is the number in front of the x. B is the number that goes along with the x. That's your slope. Like the rise over the run. That's the slope. Question. The slope tells you this, right? Which way we're laying and how steep we are. That's what the slope tells you. The A is your y-intercept. The y-intercept is the value of y when x is equal to 0. It's where it crosses the y-axis. It's when your explanatory variable has a value of 0. Okay? So it's the value of y when x is equal to 0. Okay? Now, without me showing you where it comes from, Example 5.2 gives you, see this line that's here? That regression line? It has that form, y equals a plus bx, right? A is the y-intercept and b is your slope. Okay? So example 5.2 is going to give you that equation. Example 5.2. It says, any straight line describing the NEA data in example 5.1 has the form. Now, the only place anybody ever writes words in for the variables is a statistics course where your variables have meaning, right? Remember, the y is your response variable, the x is your explanatory variable. They have meanings. You can't freak out about them putting fat gain in for the y, and the x is your NEA change, right? It says the line in figure 5.1, the line that I have here in Minitab, has the equation of this. Fat gain is equal to, what is it, 3.505 minus point, how many zeros? 00344 NEA change. There's your y, there's your x. Our variables have meaning. They write it in an example. They do that to you in some of the problems, that they want you to know that your variables have meaning here. It's just not an algebra course and you got a y and an x. Your y is fat gain, response. Your x is NEA change, your explanatory variable. Now, before we use this line to make a prediction, because that's the reason I want it, I want to make sure you understand which number here is the slope and which number here is the y-intercept. Okay? So my b here is, remember, it's the number in front of your x variable, in front of your explanatory variable. You take the sign with it. Your slope here is minus 0.00344. Now, anybody remember anything about lines? Negative slope means we're laying back this way, right? Positive slope means you're laying this way. You do understand if the correlation is negative, and so you're thinking you're seeing a negative association, that your regression line has to have a negative slope to follow it, right? Those have to go together, yeah? I mean, there's no way you're going to see a negative association and all of a sudden you got this regression line and it doesn't have a negative slope. It's not laying back to follow that form. They got to match up, okay? So the slope there is b is equal to minus 0.00344. The sign went with it. Now, we like to interpret that. Oh, remember, we got numbers in this class, but it's always numbers with a context. So, for me to interpret this, what we like to talk about is, for each additional calorie of NEA change. In general, you want to talk about increasing your explanatory variable by 1 unit. Okay? Then fat gain decreases by 0.0034 kilograms. So in other words, interpreting the slope, this statement that we're making here, for each additional calorie of NEA change, I increased your explanatory variable by 1 unit. Then your response variable, fat gain, decreases because the slope is negative by whatever the slope is. And then you always have to give me this little thing on the end here, on the average. Okay? One more time. Anytime somebody gives you that regression line and they ask you to interpret the slope, what does it mean? You always think about increasing your explanatory variable by 1 unit for each additional calorie of any A change. Then your response variable, your Y, whatever it is, fat gain. If the slope is negative, it decreases by the slope on the average. If it was positive, it would increase. Now, before I go and talk to you about the y-intercept, here's what we're talking about. Forget the little dots for a second. I'm interested in the regression line, right? That's the one that's on the scatter plot. If I start here at any value of your explanatory variable, and I come over here, and all I did was, for each additional calorie of any A change, I increased your explanatory variable by 1 unit. And if I come up here, and here, look, if you remember anything about algebra, people always, somebody gives you a line, they're always drawing you that right triangle. Yeah? This right here has a side of 1. Hell, we picked that, right? We increased the explanatory variable by 1 unit, yeah? What we're telling you is this value right here is slope. Remember, the rise over the run. You set the run to be 1, so the rise has to be the value of the slope. So whatever this value is here, whatever that value is there, you decreased by . I like to draw the picture for you because this will not be the last time we interpret the slope of a regression line. And the reason this is all going to decrease this way, that's what my arrow is telling me, you're going to decrease by that amount, is exactly that picture. And we always think about increasing your explanatory variable by 1 unit, whatever it is. So every problem I do for you out of here, whether it asks me to interpret the slope or not, I will. All right? So that's how you interpret the slope. For each additional calorie of any A change, the fat gain decreased by 0.00344 kilograms on the average. You throw on the average in there to make everybody happy. All right? And then, what was my y-intercept? My A there was the 3.505. Okay, remember that's when your x is 0. This is the predicted fat gain of 3.505 kilograms for an NEA change of 0 calories. Now look, all I'm telling you is that's your y when x is equal to 0. That's your y-intercept. Now, here's the other warning. You can always interpret the slope. Sometimes it doesn't make any sense to talk about the y-intercept. If 0 is not close, if you don't have points in the x variable on both sides of 0, you're not going to talk about interpreting the slope. Okay? Now, I'd like to do one more here. One more thing, and then we'll go home and we'll come back, and I'll tell you on Thursday how in the hell I come up with the equation, and we'll work some more problems, all right? What I would like to do is, I would like to predict fat gain for an NEA change of 300 calories. Now, what I'm telling you is x is equal to 300. Find y. Remember, x is NEA change, y is your fat gain. You have this as your equation. Fat gain was equal to 3.505 minus 0.00344 NEA change. Look, folks, instead of looking at the scatter plot and reading up and reading over, we're going to get an exact value here. You're going to plug in 300. Anybody got a calculator will tell me this answer, that 3.505 minus 0.0034 times 300. What'd you get, Tyler? Tell me it's close to 2.4, whatever I eyeballed it as, or 2.3 or something. 2.49 kilograms. There's no reading a line, reading up and reading over. That's exact, right? We actually plugged in and said, okay, when NEA changes to plus 300, the fat gain is 2.49 kilograms. You plugged in. That stops me from reading up and reading across. Now make sure you turn in your homeworks. We'll see you on Thursday. Don't forget about the 3 homework problems out of Chapter 4 for Thursday. Be careful going to the house.
Does anybody else have homework to turn in? Go ahead.
Hello? Professor Marks, Dr. Marks, sir. Hello?
Dr. Marks.
Hello?
Yes.
In my notes it says that the homework for Chapter 3 is due on the 24th.
One more time, a little louder.
Sorry, I've lost my voice. In my notes it says that the homework is due on the 24th for Chapter 3.
That's what my problem was too.
Yeah, I wrote that up and then I erased it. That's cool, man. You can bring it on Thursday. As long as you bring it and get it turned in before I post the solutions, I got no problem.
Okay,
Thank
I
you
just
so
wanted to let
much.
you know. Thank you.
All right, no problem. Thanks, bud.
See ya.